Welcome everyone to today's episode of This Is CDR. Thank you to everyone for being here with us today. Just some quick background on This Is CDR. It's an online event series we've been running for about a year here at OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals we're working on advancing in New York State and other US states, localities, and jurisdictions worldwide. Quick background on OpenAir. We're a distributed volunteer network dedicated to the advancement of carbon removal solutions essential to solving the climate crisis. Our growing global community collaborates on shared open source missions in the areas of policy advocacy, research and development, and activist CDR market development. There should be a link in the chat that you can follow to fill out a form to join our group. We get together online on Discord and plan our missions there. So please take a look and consider hopping on and joining us. Before we get started, two things that we always like to do. Number one, just some quick background on carbon removal. And to define it, carbon removal is human activity, purposeful human activity to remove CO2 from the atmosphere and to durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. Carbon removal is not point source carbon capture, which is capturing CO2 from an emission source like a natural gas or power plant or a cement plant. That is a form of emissions reduction. It's not carbon removal. So we really focused on carbon removal, which again are human activities that remove CO2 from the atmosphere and then durably store it. Number two, it's really important whenever you talk about carbon removal to be very clear up front that carbon removal is in no way, shape, or form a substitute for reducing emissions. We must reduce our emissions and decarbonize our global economy as quickly and as completely as possible, full stop. That said, there's clear scientific consensus, most recently expressed in the IPCC 6 Working Group 3 report that carbon removal will be required at gigaton scale. That's billions of tons per year by mid-century for us to have any chance of reaching our climate goals of limiting warming to 1.5 or even 2 degrees Celsius. And that's because we're not going to be able to reduce all of our emissions in a climate relevant timeframe. They're going to be hard to abate emissions. They're going to be emissions that are inequitable to abate. And for those, we're going to need carbon removal to zero them out. Additionally, in the second half of the century, we're going to need carbon removal to start removing the tremendous excess of CO2 that we've already emitted into the atmosphere, billions and billions of tons. So carbon removal is an essential climate solution. It sits alongside adaptation and emissions reduction, and it's not a substitute for either one. We'll put a bunch of resources in the chat. There's an icon in the lower right-hand corner of the screen for the carbon dioxide removal primer, which is a great place to start learning about carbon removal. We've run 40 plus episodes of This Is CDR, so there'll be a link to past episodes in the chat, and another great place to learn about CDR, and maybe a few other links there. And today we're going to learn about a very interesting CDR method. My colleague Megha Raghavan is going to hop on now to talk a little bit about run of show and introduce today's session.
Hey everyone, I'm Megha. I am an OpenAir member based in London, but working on policy advocacy out in California and the US where I'm from. So as usual, our format is going to be a short presentation followed by a few prepared questions and then moderated audience Q&A. So please type any questions you have into the Q&A box in Zoom. Just note that that's separate from the chat box. So if you could use the Q&A, that helps us to organize the questions better. The event is being recorded, so we'll send the video link out to everyone who registered, and we'll also post it to OpenAir's website and to our YouTube channel. This week on This Is CDR, we're very pleased to welcome Climate Robotics CEO Jason Aramburu to tell us about the company's mobile autonomous pyrolyzers that leverage advanced robotics and artificial intelligence to convert waste biomass into biochar and to durably sequester atmospheric carbon in the soil while improving the economics of commercial row crop agriculture. Jason Aramburu is a serial entrepreneur and venture capitalist, primarily focused on application of artificial intelligence, machine learning, robotics, and trustless computing to agriculture, mining, logistics, energy, health, and climate change mitigation. Jason was a Forbes 30 Under 30 social entrepreneur, an Ashoka Fellow, PopTech Social Innovation Fellow, Echoing Green Fellow, and a grantee of the Bill and Melinda Gates Foundation. He's also one of Business Week's top 25 social entrepreneurs in America. Jason graduated from Princeton University cum laude with a degree in ecology and evolutionary biology and a certificate in environmental studies. He has extensive research experience both in the lab and the field, having spent significant time studying and working at the Smithsonian Tropical Research Institute in the Republic of Panama and at Princeton University's Carbon Mitigation Initiative. So Jason, whenever you're ready, over to you.
Thank you, Megha. And thank you to everyone on the OpenAir team as well. Great to be here. I'm Jason Aramburu. I'm the co-founder of Climate Robotics, and I think you provided a great overview and introduction. I guess a little bit more just about my background. I've been in the biochar sector over 15 years now. Biochar is something that's been around for thousands of years. It's actually an indigenous practice originally developed in the Amazon basin as a way to improve the health and quality of acidic soils. And I would say over the past 15 to 20 years, it's become a very interesting topic for CDR and carbon dioxide removal and climate change mitigation as well. I've really been in it since the beginning of this kind of modern resurgence of biochar. I get asked a lot, how did you first get exposed to it? How did you learn about it? And it was actually, when I was at university at Princeton, I was working. My university has a partnership with the Smithsonian Tropical Research Institute in Panama, and I was working as a field scientist down there. And that's where I first learned about biochar, because it's something that's used quite throughout the Amazon basin and Central America. Farmers have been making charcoal to improve soil health for a long time, and I thought this is really fascinating. And then, I started to read some of the papers from James Lovelock and Johannes Lehmann at Cornell about the carbon removal potential, and I thought, wow, this is really a win-win. And so it became something I really wanted to devote significant efforts to. And I have worked really all over the world. I've worked in East Africa and Kenya, developing low-cost biochar kilns for farmers, and really saw tremendous results there. Saw farmers double or triple their yield of corn and sugarcane by combining biochar with chemical fertilizer or organic fertilizer, and really found tremendous results and found the technology very fascinating. And I had always wanted to bring the technology to domestic, developed world commercial agriculture, because the difference in scale there is just astounding. I mean, you look at farms in the US, for instance, the median farm size in the United States is 1,000 acres. And it's not uncommon to see 10, 20, 30,000 acre farms in the US. And, if you think about the carbon storage potential on a smallholder farm, multiply that by 10,000, it's really astounding. And I really felt, for biochar to succeed and to scale, it needs to reach commercial row crop agriculture. And the reality is, in 15 to 20 years, it hasn't yet. Today, most users of biochar are either, home, hobby gardeners, value-added farmers, so farmers who are farming very high-value crops like fruits, vegetables, nuts, trees, hemp products, and it really hasn't permeated into the bulk of U.S. agricultural productivity, which is corn, wheat, soybeans, rice. And so I'd always wanted to find a way to bridge that gap. And about 3 or 4 years ago, I was actually having a beer with an old friend, Dr. Morgan Williams, who is also, a veteran of the biochar industry. He's been involved with multiple companies. He was a Virgin Earth Prize pioneer by Richard Branson for his work in biochar, and is also a PhD soil scientist from Berkeley. And, we were just chatting and saying, hey, we've known each other 10 plus years, good friends. We've been in this industry a long time. Why isn't every corn farmer in the Midwest using this stuff? And we realized, it wasn't really a question of does it help, does it work? It was really a question of cost. When you actually look at it today, a ton of biochar costs a farmer in the Midwest, in many cases, $800 to $1,000. And that's really expensive. And in our experience, that price point just doesn't match with the benefits of the biochar, both on the carbon storage side and the agronomic benefits. For $1,000, a farmer could buy a ton of chemical fertilizers and inputs that work immediately. And so we realized, really the cost needs to come down. And so we started digging into what are the major cost centers for biochar. And the first one was transportation. Moving feedstock around to a pyrolysis plant is incredibly labor intensive and cost intensive. And then you got to get the biochar back out to the farm. And we realized that, that was over 50% of the cost to the end user. And then we started digging in deeper and we realized that, well, the reality is virtually all biochar that's sold today in North America comes from wood as a feedstock. And whether it's wood chips or wood pellets or what have you. And wood is not a free feedstock, despite what people might claim. There is a very large biomass energy market in the US. So if I'm a forestry operator and I have a ton of wood chips, there's already a market for me to sell those. And there's a floor price for that wood. And ultimately, that just drives up the cost of feedstock for biochar producers. So and of course, there's other cost drivers, but we realized those two were really the bulk. And if we could address those two cost centers, we could really develop something that could scale and could realize gigaton scale impact. And so, that was about 3 or 4 years ago, and we decided to start building. And we actually started building prototypes in my backyard. I was living in the Bay Area at the time, and we started building prototypes of what would become climate robotics technology. And we filed our first patents in 2020, early 2020, and did entirely self-funded, and really just proved that yes, this could work. And now, 3 years later, today, we have a functional, full-scale field prototype of our system. We're in market, we're producing biochar, and we have a major buyer of the carbon credits that are generated. So we have a partnership with Microsoft in place to actually buy the CDR credits. We have biochar in the ground in Texas and Arkansas currently, and looking to expand to about 5 or 6 more states next year. So what I'd like to do now is just I'm going to share my screen and tell you a little bit more, specifically about what we're doing. So, climate robotics, fundamentally, we believe that to beat climate change, we have to harness the power of the biosphere. Every day, the biosphere is drawing CO2 down from the atmosphere effectively at zero cost. Plants extract CO2 from the atmosphere and convert that CO2 into plant biomass. This gives us really unique market positioning. We're sitting right now at the intersection of what we believe to be $2 trillion industries, emerging $1 trillion industries. And, we deliver massive improvements and benefits in both dimensions there. So I imagine the audience is pretty familiar with biochar, but just as a refresher, it's a high performance soil amendment made from biomass waste. And that can be, as I mentioned, it's mostly wood waste today, but you can also make biochar from agricultural waste. A crop like corn, for instance, produces about 4 tons of waste per acre per season. A crop like peanuts is going to produce upwards of 8 tons of waste per acre per season. And in all cases, those wastes don't really have a use. They generally can't be sold as animal feed. In some states, you can sell them as bedding for dairies, but it's very low value, low profit. So the reality is most farmers just either burn the field, till those wastes into the ground, or let them decompose on the surface. And those 3 processes don't return substantial carbon to the soil, maybe 1 or 2% by mass. Biochar, when it's made properly, it's a lower cost replacement for many chemical soil amendments that farmers already buy, such as agricultural lime. It's possible to make biochar with a very high pH that can actually replace lime, which is a commodity commonly used in commercial agriculture and row crop agriculture. Biochar also is proven to boost nutrient retention, water retention, and crop yield. And then most interestingly, it's a tool to sequester CO2 for thousands of years. And so the way that biochar actually sequesters CO2, well, I touched on this already, but the normal business as usual carbon cycle on the farm, we grow the plants, they draw CO2 down, and those plants produce residues or waste. And that waste is either allowed to decompose or it's burned. Any way you go about it, 98 to 99% of the carbon in that biomass returns to the atmosphere within 1 to 2 years. With biochar, we capture that biomass waste and we carbonize it. So in effect, we're fossilizing the carbon. We expose the material to a low oxygen, high temperature environment. And under those conditions, it thermally decomposes into a very pure form of charcoal, almost more like a graphite in terms of composition. And that's a mineral form of carbon. So the original biomass is a biological form of carbon. It breaks down very quickly. Mineral carbon breaks down very slowly, upwards of hundreds or thousands of years, depending on how well you cook it. And we can touch on that later, but the conditions under which you produce the biochar have a dramatic impact on its agricultural properties and its carbon stability. So we convert those wastes into biochar, and then we add them back to the soil. And the research shows if that's done properly, we can actually sequester carbon for hundreds or thousands of years in the soil this way. And as an added benefit, we're improving the health of the soil. So that's the biochar industry. That's how biochar works. What are we specifically doing that's unique? Well, I mentioned that the two biggest problems in the industry today are logistics and transportation and feedstock availability. And so we have developed a system that solves both of those. So we're actually developing the world's first in-field biochar production system. We have developed a system that attaches to the back of a standard agricultural tractor and uses an off-the-shelf harvesting implement to harvest those wastes in field, pyrolyze them, so convert them into biochar, and then redeposit and reincorporate the biochar into the soil in a single pass. And by doing this, we eliminate the transportation requirements. We're producing the biochar right where it's needed. And two, we open up the potential to use these very abundant, low cost or even free feedstocks as opposed to wood. So our system, you can see the renderings here, but we have a functional full-scale system in our shop in Houston, Texas. It consists of an off-the-shelf agricultural tractor. We use a John Deere E-Series system. On the front of the tractor is what's called a forage harvester. This is an off-the-shelf implement designed to harvest corn waste from the ground. The forage harvester conveys the material to our pyrolyzer, which then, it's a fully self-contained pyrolyzer. It efficiently converts that material into biochar and redeposits it in the soil. And then on the back end, we use a standard disking implement that's used in agricultural every day to incorporate the biochar into the top 10 centimeters of soil where it has the greatest agronomic impact. And we're able to do this because we developed a pyrolyzer from the ground up. We looked at over 50 different companies and couldn't find an off-the-shelf system that could really be used in a mobile context like this. And so our system, which is actually now patented, we had our first patents allowed by the USPTO, covers our design of our pyrolyzer, but also our invention of a mobile continuous system. It's a 3-stage process. So in the first stage, the biomass enters the pyrolyzer where it is preheated, pre-dried, and chopped down to the appropriate size. And this preheating is actually done, it is powered by the gas that's generated in the pyrolysis process. So it's a very efficient process. It comes out of the preheater bone dry and at between 100 and 200 degrees centigrade. And that's really important because in pyrolysis, over 50% of the thermal energy required by the process is just to remove water from the feedstock, just to dry it. The second phase, which is unique to our process as well, is the actual high temperature pyrolysis stage. So what we found in our research is that the most pyrolysis systems will operate at 300 to 500 degrees centigrade. And at those temperatures, you're going to produce a biochar that has a permanence of, say, 100 years in the soil and might have a pH in the 8s or the 9s. Our reactor actually, through a unique design and unique design elements, we can actually operate at up to 1200 degrees centigrade if needed. Now, we usually don't go that high. We're usually at about 800 to 1000, but at those temperatures, we get a much more high value product out and a much more consistent product. So we get a product that is longer, has much longer durability in the soil, and actually has a much higher pH. We've produced a high pH biochar of 11 plus, which, pH is a log scale. So that's really important because one of the major costs on a farm, input costs, is actually lime. It's chemicals that farmers use to boost the pH of their soil. Higher pH soil is more valuable. It produces a higher yield. In the third stage of our process, we quench the biochar. So we actually spray it with water and use also mechanical and passive heat sinking to bring it down to a temperature of about 80 degrees centigrade. And then in the final step, we infuse the biochar with any fertilizers, inputs, microbials, inoculants, anything that the farmer might need. And from there, we actually dispense it back into the soil at a safe temperature, usually around 20 to 40 degrees centigrade. And at that point, it's safe to use. It's safe for reapplication to the soil. And there's a lot to our pyrolyzer design that I haven't covered. As anyone in the field can attest, doing any work with agricultural waste is really hard. It is incredibly non-trivial. I mean, entire companies, there was a company called Kior that raised hundreds of millions of dollars from venture capitalists to make, I think, fuels from corn waste. And their Achilles heel was they couldn't figure out how to move agricultural residues efficiently through a machine continuously, because it's very hard. And so a big component of our IP is the actual materials handling technology we use that allows us to continuously process these feedstocks in the field. So our primary market is commercial row crop farming, corn, wheat, rice. These are crops that produce very abundant dry wastes. There's actually over 1 billion acres of suitable farmland in the US, and using the waste that are present on those farms, we can generate an average of 2 to 3 metric tons of CO2 equivalent per acre per year stored. And we believe that based on third-party data and our own field trials, that translates to about $100 to $150 per acre in value to the farmer. We're also really interested in the pasture land market. We have a project with a commercial ranch here in Texas. The ranching business is becoming increasingly challenging for landowners. Demand for beef is going down in this country, and they're having to shift to, raising higher value cattle and trying to make more profits. So it's actually a really interesting untapped market because pasture land is very productive, produces a lot of biomass. And, we believe if the beef industry continues to decline, there'll also be a massive opportunity there to use that pasture land for carbon sequestration. There's quite a bit of research that shows, that we should not be converting our grasslands and our pastures into forests for carbon sequestration. We should really be using the native grasses that are already there as the feedstock. And I think it makes perfect sense. There's about 500 million acres of range and pasture land in the US that's suitable for this, and similar carbon storage dynamics and similar yield benefits. And then, of course, we are interested in the carbon removal market. And I touched on this before, but, because of the process conditions of our pyrolysis system, we are able to generate a much more durable biochar, a biochar that, we can actually generate a biochar that meets this 1,000 to 10,000 year bucket of durability. And we do that through the pyrolysis conditions that we employ, also the use of certain catalysts in our process that increase the yield of stable carbon. A lot of people ask us, is this something you can do year over year to the same acre of land? And the answer is absolutely. The liming benefits of biochar are consumed. So after a year, you do want to add more biochar to get that liming benefit back. The water and nutrient holding benefits, those do appear to be very long lasting and permanent. We have tested at the equivalent of about 120 metric tons of biochar per acre. We found no negative impacts on crop yield. And then in the literature, folks have actually tested it up to 200 metric tons and gotten similar results. So suffice to say, you can do this year over year for decades, if not centuries. If you asked my colleague Morgan, the soil scientist, what his thoughts are, he would probably say it's more like thousands of years. There's really not an upper limit to how much fixed carbon you can store in soil. But we believe, based on this data, there really is the potential for 1 billion plus removal tons per year in the US alone as biochar. We also believe this is a massive market around the world. The US is obviously the largest agricultural market by value in the world, but what's interesting is in places like Australia, China, Western Europe, they have massive problems with soil acidity. Farming practices and just geology have led to a drop in soil pH across those regions. If you look at China, almost all of their agricultural land is considered acidic. In the US, it's probably more like 50, 60%, but in China, it's nearly 100%. And so the need is really there for low-cost soil amendments that can address that agricultural problem. And, as a consequence, it's also a great way to sequester carbon. So when we look at all the developed agricultural economies around the world, we calculate a total addressable market of over $60 billion for these types of technologies. And that market will only grow as the carbon removal markets heat up and continue to expand. So that's a really short summary of what we're doing. Excited to dig in and answer your questions. In terms of what's next for us, now we're really about scaling up. We have our working system, our prototype. It's taken a lot of time to get here. We've had to develop multiple generations of prototypes and systems to really get this right. We filed our patents, we're protected there. And so now, we're looking to scale up. So we're going to be building more units to meet the demand that we're seeing and to really grow our revenue pipeline. In parallel, we're engaged in field trials with a group called Farmers Business Network to really validate the commercial benefits of the biochar in these geographies where they have acidic soils. So we have a trial in Arkansas now, and we'll be expanding that to a number of other states next year. And then, we're continuing to grow our team as well. So I know there's a lot of folks on here that are looking to get into the field. If anybody's interested to collaborate, would love to talk to you. So just check out the website, reach out to me, or send me a message, and would love to collaborate. So I'll stop there and look forward to answering some questions.
Jason, that was fantastic. A really compelling presentation, and well done.
Oh, thank you.
Thank you so much. We have a couple of prepared questions from OpenAir, and then we have a bunch of audience questions that Megha will hop on shortly to start posing. And everyone, please continue to put those in the Q&A box. First thing I want to ask you is, if we're just isolating your pyrolysis process, can you talk about the carbon efficiency of that process? I think that's one thing that not everyone understands. So, not talking about transport, which you guys are largely obviating, or powering the tractor or anything else, just the pyrolysis process. If you start with a ton of CO2 equivalent in feedstock, how much CO2 equivalent comes out in biochar? And then what happens to the balance?
Okay, so I'll use slightly different numbers just for ease of math, but I guess first what I would say is what's unique about our process is it's actually powered by the tractor. So our pyrolyzer is powered by the engine of the tractor. So we're not like using diesel fuel in a generator to run the pyrolyzer. We do use a little bit of propane to start the system, and then we use a pilot burner just to prevent, just for safety purposes, really. But it's something like 0.5 kilogram of propane per hour. So it's really not a lot. And in our system, we're replacing a light or an inversion till. So the farmer would be already driving their tractor down the field to till and mix up the soil.
Yeah.
We're still doing that. We're just adding in the biochar. So the actual, call it parasitic emissions are quite low when you think about it that way. But so let's say on a typical acre of corn, you will have 4 tons of residue that's available. And of that 4 dry tons of residue, we can realistically harvest 3 tons with off-the-shelf harvesting equipment. We would really need to custom design a harvester to get more than 3 tons. And to be honest, you don't want to remove 100% of the stover from the ground. So 3 tons per acre comes into the system. Of that, our yield of biochar is about a ton. So for every 3 tons of feedstock that comes in, we'll get about a ton of biochar out. And the remaining mass, the difference in mass there is really the combustible gas. So the other 2 products of the pyrolysis process are combustible gas and combustible oil. The oil actually comes out as a vapor. So we have an onboard flaring system that efficiently burns that combustible material. And that's what we use as a heat source for the process. So by mass, from 3 tons of feedstock, you would end up with 1 ton of biochar. Now, to translate that to CO2 equivalent, it really depends on the methodology that you use. So there's right now 3 methodologies that are in use today, commonly for biochar. There's the Vera, there is the European biochar certificate, and then there's the Puro.Earth certificate. And it's quite a large range, actually. So from that 1 ton of biochar, depending on the methodology you use and the parameters, it could be anywhere from 1.7 tons of CO2 equivalent all the way up to 2.5 to 3 tons. So there's still quite a high variance based on methodology. And really the reality is the buyer of your credits is the one who determines which methodology you use. So yeah, they'll say, okay, I want to use the Puro, or I want to use the European, or I want to use the Vera. And that ultimately determines kind of what your yield of carbon is.
Could you baseline like I know it varies, but on a percentage basis of carbon in to carbon out, like how efficient is your biochar process if you just look at carbon in to carbon out?
I think it's about 50% in terms of carbon in to carbon out. Would need to get you some more exact details on that.
I'm just trying to, and some of that is emitted, and then some of it is used. Well, some of it's used to power the tractor, but the balance is emitted.
Yeah, exactly. And and it's important to also note that all of these methodologies, they consider emissions from the emissions of cleanly burning your syngas and your oil. That's carbon neutral because the carbon that you're burning was drawn down from the atmosphere first.
Yep. Cool. Thank you for that. So one other kind of tough question so the 1,000-year durability claim or the 10,000-year durability claim, I mean, as you know, that's much higher than other biochar claims. You talked a little bit about why your process results in that claim, like the high heat, et cetera. Can you talk a little bit about how you are going about validating that claim and validating it for buyers and carbon markets and things like that? Just because it's unique, because no one else is talking about having, and it's fantastic. I mean, I'd love for it to be true, but like can you talk about the process by which you're going to validate that claim?
So today, the easiest way to measure and validate the permanence of a sample of biochar is by measuring the oxygen to carbon ratio of the biochar. A lower O to C ratio means your biochar is closer in composition to fixed carbon or graphite. Now, most buyers of CDR credits today require an O to C ratio of 0.2 or less, which translates to 100 years or more of permanence. And this model was developed by a USDA ARS researcher named Kurt Spokus. He's been working on the model since 2010. And the way he developed the model was he actually took data, he's taken tens of thousands of samples of biochar, run them through advanced analytical techniques like NMR, chromatography, a variety of advanced techniques to determine, the actual physical and chemical structure of the biochar. And then he has built a model correlating that very precise data with O to C ratios of those biochars. And he found a really clear trend that, the lower the O to C ratio, the greater the permanence. When you get lower than 0.1, you go from 100 years of permanence to 1,000 year plus, or it's considered 1,000 to 10,000 years. And we've had our biochar tested by a number of groups, including Texas A&M University, and we've met or exceeded that threshold.
Okay.
Now, it's really a function of several things. It's a function of the feedstocks that you're using. It's a function of the pyrolysis process parameters. So specifically the temperature at which you operate, the residence time, so how long the biochar is actually subjected to those temperatures, and the oxygen concentrations in your reactor. A fourth contributor, which we have developed internally and spent quite a bit of time on, it's actually the use of catalysts. So by combining your feedstock with certain catalysts, in our case, these catalysts are materials that are commonly used in commercial agriculture, are very low cost and very abundant. There's actually quite a bit of data now that by combining the feedstock with those materials and pyrolyzing them together, they have an additive effect. It actually catalyzes the formation of more fixed carbon in your biochar, which ultimately increases the overall permanence of your sample. So it's really those four process parameters. And I would say the temperature, residence time, and oxygen concentration, that's pretty well known.
Yeah.
The catalyst stuff is really cutting edge stuff.
Cool. And so the O to C ratio is a discretely measurable variable factor. And then that's used as a proxy for durability.
Exactly. It's used as a proxy for durability. And, what I am seeing in the industry, I am seeing groups asking for a new test, because O to C, it was really intended to be kind of a down and dirty test that any soil lab could do. That was the idea behind it, so that, if you're in the middle of North Dakota and you need to test some biochar, you can go to the local ag university and get it tested. What I'm seeing now is there's a lot of groups, like we have a colleague, Carrie Masiello at Rice University, who are actually trying to scale the more precise analytical techniques like NMR, because those are much more precise. The challenge is just not every university has that capability. But, in 12 years since Kurt started working on this stuff, the costs have come down to run those tests. So I do think over the next 5 to 10 years, we will see a shift from, this kind of down and dirty proxy test, which, is really meant to do anywhere, to a more specialized, high precision assay.
Got it. That's great. Thank you so much. And well beyond my pay grade, we do have a couple of biochar experts in the audience who've been asking some of these questions. So there may be some follow-ups. And I had one more question about modularity, but I will just say, instead of asking it, just say we're huge fans of modularity, and the fact that your process is distributed and modular, we think it's a huge asset to what you're doing. So that's really, I think, well thought out. But Megha, do you want to come on and start working on some of these audience questions?
Yeah, sure. So I think since we were talking about durability, there were a couple of other questions around that. So could you just talk a little bit about what actually causes biochar to decompose? Like, what are the agents of decomposition? How does that interact with the oxygen-carbon ratio you talked about, as well as like, soil conditions, humidity, generally the environment that you distribute the biochar in?
Mm-hmm. Yeah, so it's important to think about biochar not as biochar you're producing in the field. It's not a homogeneous product. It's really a heterogeneous product. So your biochar sample is going to have a mixture of ash. It's going to have fixed carbon in it. Fixed carbon is really more like a graphite. Fixed carbon is arguably durable for tens of thousands of years. And then it's going to have some kind of spectrum of labile carbon and faster decomposing carbon in it. So basically material that's somewhere between an ash completely burned and a fixed carbon. And it's that section of labile carbon that really determines the permanence of your biochar. And that's what this O2C test is ultimately measuring. It's measuring how much, fast decomposing carbon is in your sample. Now, what causes the decomposition of that fast decomposing carbon? It's a few things. I mean, it's physical weathering, so the soil actually physically breaking it down over time. Also, just microbial activity. Microbes in the soil will act on labile carbon and break it down. So it's really those two factors are the bulk of the sources of decomposition.
Got it. That makes sense. Okay. And actually, just going on from that, since you mentioned it, we had a question about sort of those other products that are produced. So, as you said, pyrolysis will generate ash and potentially some other products. So out of the 100% biogenic waste that you put as an input, how much of that turns into biochar, and, what kind of other products come out in the rest?
Well, it really depends on the pyrolysis conditions. And one unique aspect of our technology is, we can control our operating temperature to a degree. Even a tenth of a degree if we need to. So we can very precisely control all the pyrolysis conditions. And those conditions are just going to influence the yield of all these different products. So with our current system, we're optimizing to produce high quality biochar, but we can tweak the system to produce more oil or more gas as we see fit. We can also tweak it to produce ash. So really, it really depends on the process conditions. At this point in time, the best economic product, or the most economical, is to produce high quality biochar.
Okay, got it. And then just one last question on the durability side. As Toby mentioned, you guys are going for a much higher durability than most other biochar projects are. Are you getting acceptance for the durability numbers that you're putting together, or is there a pushback on that as you start to think about commercializing?
Yeah, I would say we definitely are getting acceptance, and you want to push for higher permanence for a couple of reasons. One, the credits tend to be more valuable, and two, it's just ultimately better for combating climate change to deliver a higher permanence removal. Now, I don't think low permanence removals are bad. We really need a basket of solutions. The reality is there's not enough money out there to fund 100% permanent removals. It just won't work. That would really, it's just not feasible. So the reality is we do need a basket of solutions, and it's also the reality that the yield is lower when you produce higher permanence biochar. So in effect, it costs more to produce a ton of higher permanence biochar than a low permanence biochar. So, and that's really part of the reason we designed the reactor the way we did. So if we have a credit buyer that says, we want 100 years of permanence and we'll pay that price, we can actually adjust our process parameters to make that type of char as well. So it's really, we really designed this to be a market-based solution.
Right. Okay. All right, we had a couple of questions about the process itself. So the first one being, what kind of pre-treatments are required, and sort of what kind of issues are they addressing when you need to pre-treat the biochar? I know you mentioned it briefly in your presentation.
So you want your feedstock to be kind of at or below 20% moisture. So what we like to do is harvest material usually about 1 to 2 weeks after, the combine harvester or whatever they're using to harvest the grain has passed over and cut the residues. So we like to let the residues dry in the field for a little while, because otherwise, you're just spending BTUs to dry that material. Now, 20% moisture feedstock, it looks bone dry, but it still has quite a bit of water in it. And yeah, as I said, it's still about half of the thermal energy that's required by the pyrolysis process just goes into dewatering. So that still is pretty energy intensive, but I would say moisture content's really the big factor. You would not really want to do this with like food waste, for instance. So moisture content's important. Particle size is important too. Our process really requires a particle size of 1 inch or less. So we have integrated biomass processing and chopping systems in the pyrolyzer. If you're using something like trees, for instance, as your feedstock, you would need to chip that down to size first, using a wood chipper or something. So yeah, moisture content's really important, and then particle size is really important. And then third, you want to make sure there's no contaminants in the feedstock. So you wouldn't want to use material where you didn't know the source of it, for instance, because if there's a lot of heavy metals in your feedstock, for instance, they're going to become concentrated in the biochar. So in our case, using agricultural residues, we know that feedstock is safe. We know how it was grown, etc. But you wouldn't want to use some feedstock where you didn't know that in the first place.
Yeah, okay, makes sense. And then just thinking about how quickly this goes, is the tractor speed limited by how quickly the biochar module works, or could you just talk about how quickly it processes?
Yeah, exactly.
Based on acres
The forward speed is determined by the capacity and the throughput of the reactor. So right now, the forward speed of the tractor is about 3 miles per hour. As we build bigger reactors with higher throughput, we'll be able to increase that. But yeah, right now, that is determined by how quickly you can move material through the pyrolyzer.
Okay, got it. And then on the pyrolyzer itself, what's the source of the energy for that high temperature heat that you're getting? And as well, where's the water sort of kept, and how much do you need for the quenching side?
So the power to run the pyrolyzer comes from the tractor itself. So commercial tractors, have onboard systems to power attached agricultural implements. And so we're actually using that. So, we're not having to power the pyrolyzer with a separate generator or what have you. So most of the heat that is required for the process comes from the burning of the syngas and the bio oil. We have integrated burners, that transfer heat to the pyrolyzer. And then, so with that type of fuel, that's how most, existing pyrolyzers work today, or some form of that. You'll be able to get your feedstock up to 300 to 500 degrees centigrade that way. But to really get to these high temperatures, you need additional, high density or high watt density heating systems. So we actually use a custom system based on magnetic induction to provide kind of that extra top off of heat. And we chose induction for a couple of reasons. One, it's the highest watt density of any heat source or any commercially available heat source. So you can take material from a low temperature to a high temperature very quickly. Two, it's a very efficient way to heat. And three, it's dynamic. So you can quickly raise or lower the temperature with induction almost instantaneously. And all of those three are really critical to actually doing this and making this work in a continuous process.
Okay, got it. We got a few questions about life cycle analysis. So maybe you could talk about that broadly. I think the specific questions were about the LCA of like the steel and other parts that you need in terms of constructing the units, getting the units to the farms, things like that, as well as any sort of secondary effects. You know, if you add biochar to the soil, how does that affect the soil's own ability to retain or absorb carbon?
So we're still kind of going through the LCA as part of these certifications, but what we do know is that LCAs have been done for similar sized agricultural equipment. The general figure is around 17 tons of CO2 equivalent to make a similar system. And, you know, to put it in perspective, I mean, one of our units at scale, you know, it should be sequestering 2,000 plus tons per year. So really, you know, the embodied emissions of the steel are quite small, we think. Obviously, we'll validate that with a full LCA, but we believe based on, you know, industry figures, it's probably pretty small.
Okay, got it. And what about, you know, you were talking, the other question was about like how it affects soils and plants and their ability to retain carbon as well?
Well, you know, there is a study, it came out 1 or 2 years ago, and it's a meta-analysis of 153 peer-reviewed field trials of biochar. And what they found was a grand mean crop yield improvement of 16% after application of biochar. And that was irrespective of soil or crop type. And it's a very robust, very well done study. There have been meta studies in the past that were very poorly done, in our opinion. This one is very well done. And based on that figure, yeah, I mean, if your crop yield increases 16%, you know, your crop is going to be drawing down 16% more CO2 as well. So I think there probably is a secondary additive effect based on that and carbon sequestration. There's also likely secondary effects around, you know, reduction of lime consumption. I mean, lime is a soil amendment that by its nature releases CO2. As lime breaks down over a season, the calcium carbonate converts into CO2 and gets released. Those secondary avoided emissions are not captured in today's methodologies. Hopefully in the future they will be, but you know, they're not today.
Okay, got it. Just going to ask a couple more. So we had a few questions around the revenue side of things, and I think I can kind of boil it down to like just how do you see the revenue flows working in this industry between, you know, you guys, the carbon markets, farmers, potentially like tractor manufacturers, you know, who do you think is paying who in that equation essentially?
Yeah, so right now our model is to own and operate the equipment ourselves. So you know, we operate it, we contract with the farmers to do this, and then we sell the carbon credits. And today, you know, the carbon prices are high because demand for durable credits greatly exceeds supply. We expect over the next 5 years, supply is going to increase. There's lots of companies looking at different ways to durably sequester carbon. So, you know, based on that, I would expect the price to come down over the next 4 years. So we're really working to improve our efficiency and reduce our cost. Today, we pretty much need 100% of that carbon revenue, you know, to fund like the prototype development, getting it out into the field and operating it. But we do have a path to really drive down that cost through efficiency. That comes from just automation. So labor is still one of the biggest costs for us. You know, you need someone to drive the tractor, you need someone to man the pyrolyzer. But we're seeing commercially available automation technologies really come to market quickly. You can now buy an off-the-shelf kit that will drive your tractor up and down the field automatically. And in 5 years, there's going to be a whole basket of solutions there. So we really see automation as the key to get the cost way, way down and to really remove the human labor requirement. In terms of kind of the relationship with the farmer, we contract with the farmers. You know, we today are providing them the biochar as the benefit. They're getting the agronomic yield. We do believe as more data comes in around biochar's impact in these commercial row crops, we'll actually be able to the farmer will take on a share of the cost as well and really pay for some of that benefit.
Got it. Okay. And then last question, which we got from a couple of people. What do you see as kind of the major bottlenecks when you think about scaling up, and what are the key things you'd like to see to alleviate those?
Well, I think one is just supply chain challenges. I mean, we're building heavy agricultural equipment, so finding reliable supply of parts is hard in today's environment. We are starting to see that ease up. Also, energy prices. I mean, diesel fuel to run these tractors is quite expensive today, and hopefully we can bring those costs down over time, and hopefully they come down. Of course, doing anything with heavy mobile equipment, it's just challenging. It takes capital as well, but we're seeing that there are now non-dilutive sources of capital to fund these types of projects and scale up. So, I think while there are bottlenecks, we are seeing them improve. And then, on the other side, it's really just awareness and acceptance. Today, row crop farmers, they're learning about biochar, but still many of them don't know about it. And so really educating them on the benefits, why it's good, why they should use it, I think that's really critical.
All right, great. Thanks so much, Jason. This has been amazing. And
thank you.
Toby, back to you to close this out.
Thank you, Megha, and thank you all in the audience for such great questions and for joining us today. And Jason, that was really eye-opening for me, and I learned a lot. So
great.
Really appreciate you being with us, and look forward to learning more about what you're doing and following along as you advance the climate robotics business in the biochar field. So good luck, and thank you again.
Thank you. Appreciate it.
Just a couple notes on what we're up to with OpenAir and what we have upcoming. We're very excited by federal activity from a legislative perspective on carbon removal. And there's a bill called the Federal Carbon Dioxide Removal Leadership Act that has a lot of key elements that are also in our state level CDRLA policy. OpenAir is working on a nationwide citizen lobbying campaign for the federal CDRLA. So if you live in the United States, anywhere you live, we can connect you with a team to reach out to your local representatives to get them to learn more about carbon removal and hopefully sign on as sponsors for this bill, both Senate and House. So please, if you're interested in helping us with this, again, there should be a join OpenAir link in the chat, and we'd love to have you be a part of what we're doing. And we definitely, the more hands on deck, the better on all of these things. And then in terms of This Is CDR, we have a couple great sessions that we actually just announced that are coming up in August. On next Tuesday, the 2nd, we have Project Carb Down, which is a European enhanced rock weathering initiative being funded by the Carbon Drawdown Initiative. And basically they're making some really interesting advances on enhanced rock weathering MRV, which is obviously critical to making mineralization work for carbon markets. So excited to have those folks on next week. 2 weeks from now, we have Carbion, which is a Dutch direct air capture company, X-Prize milestone awardee, doing some very innovative and novel approaches to direct air capture. The 16th, we have Inner Earth. They are an Australian-based biomass burial company working on a novel approach to burying biomass, raw biomass, and for durable carbon sequestration. So excited to hear from them and learn about what they're doing. And then on the 23rd, another biochar company, very different from Climate Robotics, a Finnish company called Carbofex, and they're working on large industrial biochar systems to generate biochar for carbon removal and also renewable energy. A bunch of great stuff coming up this fall. We have Travertine booked. We're working on a session on ocean MRV, which is really critical, and others. So please follow along. You can follow us on Eventbrite or on Twitter to kind of be aware of these as they come out, and please register and join us. So again, next week we have Carbon Drawdown Initiative. Thank you all for being with us. Thank you, Megha. Thank you, Chris Neidel. And thank you especially to Jason Aramburu from Climate Robotics for such a great presentation. Be well, and we will see you next week.